Yeah, I will start the classes. Yesterday we were talking about and remaining part it is just an assumption of okay. Yesterday we talking. Let me come yesterday. Let us revisit the last classes. Uh, Look back what really has happened. We just dealing with the conversion of okay exactly the conversion of that is a continuous AWG channel into what exactly the vector channel, right? So as I mentioned, x of t is equal to si of t. Okay, exactly. Si of t is equal to noise. Si of t is the input and noise. Okay, exactly. So this si of t noise will be introduced here. Xi of t is this, okay, and this will be mapped with the probability from the map receiver will represent the given signal in the signal space, what we call geometric signal space, in which it will determine the energy of a signal by using Euclidean space, what we call it as signal space or a geometric representation. From that, it will be identified with whether the received is correct or not, with the probability m function, which is absolutely mentioned in the m into n matrix. Okay, exactly m into n matrix. Okay, exact m into n. Okay, m into n matrix. M into n matrix. Then when you come back to this, as I know that, as we told, Si of t is equal to, okay, Si of t, Si of t is equal to S1 of 2, comma S2 of 2, and so many other things. Like, similarly, Xi output, if you say the output of the receiver as absolutely here, Xi of t is equal to X1 of t, X2 of t, Xi of t, I is equal to 1 to the power of S1 of t and X2 of will combine. How we are going to determine, which we already told, the each elements of the input. Okay, each elements of the input will be mapped into the each element of the output. That is, for example, x of t is equal to x1t. X1 of t will be mapped with s1 of t with the help of the bias function over a time period of the signal is transmitted to the receiver. So that means the output of each subset signal has to be matched with the bias function. That is why we represented this. This output has to be represented, has to be summation and the noise, as we mentioned there. And when you go back, see, this is the signal which you already know what is SI of G and pi J. And in order to calculate the energy, for example, as I told you that it represent the signal of represent the received signal in the Euclidean space. In order to calculate the energies, this energy has to be calculated with the help of what exactly? This is with the help of the equation that is derived from the gram schematic derivation, orthogonal procedure derivation, where it will be able to calculate the what length of the signal, which is also called as energy of the signal. Okay, so that we have find out. So when you use any x of t is equal to x1 of t, any sample of the output is equal to what? Absolutely, we just mentioned it's across this values. We mentioned this values here, and when you mention this values, we'll get back to the noise. That is, any one of the element x of t is equal to, this has to be is equal to noise. That means signal while going to this is does not get affected only because of the noises get affected. Okay, exactly. Then look back here, this equation, the output is equal to what? We derived so far, this output is equal to input plus noise. This is the input, Si of J is equal to the input here. See, look back here, the input is a constant because it is transmitted from the transmitter to the channel. It is just generally it has to be constant. We do expect that, but some of the signal is get corrupted due to the what exactly? The unwanted signal, what we call it as a noise, absolutely present in the channel. So channel, as we choose an AWG channel, what will happen? The noise has to be constant. That means it has to be independent of the frequency, which means that when the signal, there is an information signal which is crossing from the transmitted to the receiver, absolutely will be a constant absolutely information signal will be what we call it as some information signal. Okay, exactly. The information signal only just get multiplied with the magnitude of the noise, it does not get changes. But generally in AWG channel also some little extra noises will be there. Even though we define noises, what AWG channel we know it is just integrated of all noises, but some little noises there is out of control even in AWG channel. That means noise absolutely varies as the signal is moving from what I call transmitter to the receiver. So some kind of noises varies. That is unpredictable. We can say unpredictable. Therefore, the output of the, even though this output of the signal is, look back, output, this output of it depends upon the input, which is constant. The white noise, as we mentioned now, right now we mentioned that there is something random, changes, unpredictable. When you say unpredictable, it has to be what exactly? Noise changes. So due to the noise absolutely changes here, we call it as, this equation has to be analyzed with respect of the what? Randomness. That is what we are here. The equation number, that is out, equation number 20, that is output is in a random nature, stochastic condition due to the noise in the channel. Thus the output of the signal in the AW channel is a random in nature. Therefore, what exactly we need to analyze the equation is stochastic condition, that is statistic condition, right? So that means the output x of t is equal to input and plus noises has to be analyzed with respect to the what exactly? Stochastic condition. That means we have to analyze with the help of the random in nature. Random in nature is absolutely what? Nobody knows how exactly it behaves. That is what we call as a random nature. That means as the signal is flowing from transmitter to the receiver, the signal as it flowing, noise will also get varied. It might affect the what? The noise signal is flowing across that. That is what exactly we need to characterize. What are the character parameter which absolutely the noise is in a random nature, which slightly affects as the signal is moving from transmitter to the receiver. We call it a stochastic conditions characterization of the what? Correlator output. This is exactly the, what are the characteristics, how the noise is very we are going to deal with. Look back, basically I mentioned it. This is the n is such of a correlator output, that is small x of t is equal to x1 up to x2. Already mentioned it. Some of the signal is x of t, xj I have taken as what exactly? Variable. Some of the sample of the output is called as capital X of t, which is the, we need to analyze, this has to be stochastic process, and that means we need to analyze this is in a stochastic process. So when you say x of t is taken, this is output. The output is has to be in analysis what exactly? Random in nature, that is random variable. That means particular output what we have taken, we are going to analyze with the help of that x of j. And a similar C output is equal to, this is, if I say this is a sample of the output, that is small x of t is equal to one of the element, that is one of the element of the output, that is capital X of say, which is to analyze this. And as you know, this is has to be, this x of t has to be the summation of the input and output. Input is, as we know, that is a constant, we are going to send it. You do expect input does not change as a flowing, but it get affected due to the noise. Noise is, that means when you say x of g is not a variation, noise is also a variation. That is why we mentioned w is a random variable, represent the sample where of the Gaussian loss component. So that means wj x of j is the one of the factors, the random nature, which to analyze x of t, which is the sample of that. See, what are the factors? Characterization, as I mentioned, is for a momentum, as I mentioned it, it is, I'm going to do it exactly with the two factor, random in nature, two variables. One is exactly what exactly, there is a look back here, mean and what exactly variance. Any random nature, any random variables or random functions, whatever it may be, whenever we analyze it with respect to 2 point and mean and variance. With respect to our digital communication, we analyze the noise variation in the channel with respect to what? Mean and variance. Absolutely, the mean and variation is exactly mean and variances. Therefore, we need to analyze capital X of t, that is exactly capital X of t is this, and x of j and wj with respect to mean and variances, that is mean. So that means, but look back, very important we have mentioned, we have considered, we are dealing in this chapter as with respect to what? AWG GN channel. Okay, that means additive wise Gaussian noise, this channel, we assume that noise over the channel has to be constant. Exactly, noise over the channel has to be constant, because noise magnitude is constant. Since it is a noise magnitude is constant, and also it is independent of the frequency. That means when you say noise is a constant, where noises along the channel, it absolutely, it means that mean of the noises along the channel, that is from the transmitter to the receiver, it has to be over the mean, it has to be 0. Please mind it here, the overall noise is a constant, and hence the average mean of the noise is 0. So this I'm repeating, as we know that mean value is capital X of j. Yesterday I've done this, I'm just repeating this very important point, is that x of j is equal to si of j. Just substitute back to this and all simple. So that means mean of the noise in the channel at any point of a 0 is always absolutely zeros. Okay, exactly, you mentioned it. So similarly, the variance function is used in variation of the noise in the channel. Okay, exactly, which is given as for statics. So variances of the equation is given by, that is absolutely mentioned in chapter number 3 of the what I call salmon actings as for define our syllabus. The variance of this is equal to VAR x of j. What is x of j? We have already find out it. X of j is this values, that is variable minus square, and substitute, as you know, x of j is equal to that is output is equal to input plus output plus noise. So when you take this equation for our random variable, that is capital J, which is considered one of the sample for analysis of capital X of, this is X minus J. We substitute back to here, we will get back to this. So we finally, this is the noise is over a bias function which I define it, just substituting here, and this two equation, look back, we are just integrate and change because same in, we wrote a into a square as this. Two functions are quite different. That means I and k are different. Look back here, I and u here. I'm sorry, exactly u and here is exactly u and I are quite different here. Two factors here. So that means expectation of this u and I are quite different. So here, what will happens to do this? This has to be what you have to do along with it, what I call it autocorrelation, because two function, see, look back here, W2, WE are two function. Within this are two, A squared has a two different values, but within that, so we can say that U and T are a different function. When you say different function, well, depending upon each function can be analyzed with the help of the what exactly autocorrelation functions, that is absolutely given, or W T comma U, the autocorrelation function, all of this is equal to this, and substitute in the R of R U of T minus is equal to N by 2 into T minus U exactly. So when you mention all these things, just substitute N by 2 spectral, we're just taking it out. So look back, the variance of the signal is only dependent on the spectral density. Two things. So what is static characterization of the correlator output? We analyze the noise in terms of what exactly two factors. That is, one is mean and variance. Mean is depends upon what exactly the input, but variance is depends on the noise only. Okay, so that is absolutely. So this is absolutely, see, two function x of j and x of k, which is used in the last equation, is quite different. So when you say two different function are uncorrelated, we need to find it with what exactly covariances, that is COV x of j and x of k. Substitute back to this, the x of j is the same value, and x of j, this is the value is given by absolutely with the help of, this is the value, this is the equation given by our statics theory, which is COA, and substitute back. It's all a simple, we are multiplying this. This is already, we know in the last page I mentioned it, x of j, we just substituting, since x of y of wj in terms of what exactly, in terms of the bias function of this and this, we'll get back to what exactly. So substitute when you get correlation, covariance that depend upon x of j. Look back, we substitute here. We know this is the value. Just substitute back to that equation originally. N by 2 into 0, it becomes, that is, the Gaussian random variable will statistically independent to each other. That means this, just repeated, this is the one derivation is a very important fact. So look back yesterday. So this is simple. Now let me, what we are going to do here, look back here. This is the transmitter. Just look here. Transmitter will come to the, through the channel, will come to the what exactly, the receiver. Capital X, this is the capital X, X1, X2, X up to the X1. It is the input to the receiver. From the input to the receiver, what will happen? Receiver, as I mentioned, two function. One is absolutely observing the information is correct. As simple as that, it checks the some priority condition. Maybe as we mentioned, as I am mentioning that from the last classes, the clock pulses of the transmitted signal has to be the frequency of the clock pulses of the watt before the at the transmitter before sending the information. If that is okay, it will go to estimate. Now this estimation will go here. This is the input received at the input of this. This is as we define the vector and find a variable. This is absolutely, we are going to define x1 and x2. We know that element of x are statically independent, which can be expressed in the probability. So look back, this, as I mentioned it, how exactly this is the input to the what the receiver, x1, x2, xn. See, look back, this comes, we once the first point, the first function of the receiver gets over, the second is estimate the things. Okay, exactly. Estimate the things will absolutely go. That is, we know that element of x are statically independent. Okay, exactly. Here, how this goes, this is the input at the receiver. Absolutely, it's going to be mapped with M into N, as I mentioned. M into N matrix will be represented in, please remember that, it will represent Elizabethan form, while Elizabethan space signals, what we call as a signal space, where we know to find of the energy of the signal, which we mention here. From there, that receiver will identify that. That means what we have so far is seen the procedure of the procedure followed by the receiver to identify or estimate the signal is correct or not. It's only by using what exactly probability function, that is M1M. We call it as in terms of statistically, we call it as probability density function. That for the element of X or statically element of absolutely, because these two are the information, capital X1 we are the statistically independent, and which are the probability density vector function, which is corresponding to the signal, very mental. That means each values are independent, each one will be independent without exactly probability density function. How we are going to do probability density? With the probability variables M1, which will be brought in that of what exactly in that of M into matrix. So now how this mathematically will be calculated? So that means what we know that capital X of n, capital X is equal to x1, x2, x3, which will be analyzed with the help of that exactly probability density of all the element of X, probability density of all the element. Look back, this is capital, the small fx, prefix x of this is the equation given by what we call or statistics probability theory, statistics and probability theory. This is the equation. Look back here, this equation, look here. Now let's come back with respect to our what we call capital X is equal to small x is equal to xj. So look back, this is one of the element of capital X is equal to small x. So each small x will have to analyze with the help of the what exactly random. Look back, please mind it. The small cap any element capital X, which I mentioned in the last page, capital X is equal to x1, x2. Each x will have input plus output. Input is a constant, but output, but the noise is exactly varies in a random nature. That means we need to analyze each bit x1, x2 also in a random natures. Okay, exactly. For which we have mentioned vector s and scalar. They look back, and these are the vector, one of the element of the sample of that among that, and small x prefix j, the random value with respect to this. See, capital X, the vector, the capital X we call it as observation vector, is also called an element of vector, and equation 4 as the what I call it as this xj, very important. It is the sample of the capital X, which is the input at the receiver point of view. So look back by Gaussian variable, we have mentioned it very clear. Whatever the noise, since we have chosen the channel is the AWGN channel, and we have clearly mentioned whatever the noise here, it has to obey the Gaussian distribution, work exactly the Gaussian distribution. So that means Gaussian distribution has been given in this form. That means this is the equation, has to obey by what exactly our noise Wj. That means output. Okay, that means the output x of t is equal to input plus output noise. Okay, so input has to be verified with probability density function. That is, it should be in the form of the Gaussian. So the input of the form is this. That means probability density of the function used by the receiver in order to check whether the received input s1 of 2 comma s2 of 2 s of 3 will be received is perfect, which is in the form of this. So this has to be, that means output has to be input and this thing. So input of this will be has to match with what exactly the probability density of function. So this will be replaced by this, because look back here, capital X, once again I'll just remember just telling to you, capital X is equal to x1, x2 up to the xn, which is the input at the receiver, which is each element is the combination of the input plus noise. The each input will be verified by whether the received input is correct or not with the help of the what probability density function. The probability density function has to obey the Gaussian distribution. Since we are used the channel is equal to what AWG, that is additive wide Gaussian channel. The Gaussian channel, which are the noise distribution, is equal to what exactly is the over the noise distribution is equal to 0. Okay, so that means whatever the signal as received, this signal will be analyzed whether corrected by the receiver with the probability density function. This look back, this may be, which will be, let me this is exactly the mathematical form. How the procedure is followed, Please remember, procedure will be followed is a different. That is in the matrix, that matrix will be flowing, that matrix will be absolutely mentioned in elucidant space. This probability density function will be implemented in the signal space. Please keep it. And second point of this, if you say this is output, input has to be matched with this probability function. The second is absolutely what we call it as a noise. This, as we mentioned, what exactly the noise? Noise over the, see, look, but basically what we are interested in exactly in the channel between the source and the destination point of view. Over noise has to be constant as for AWG, but it's still extend, still it get changes. So what we have to do over the mean at, that means at every point of the mean of the signal is only depends on the signal, does not depend on the noise. So what exactly? So overall we can say the noise is in the AWG channel is 0. That means I can put this equation absolutely what exactly is 0. Okay, this will look back as WF1. This is very clear. This is over a sample of this. W, I take the sample is just I have taken a TK of the noise W dash, and it implies that X of J, X of 2 is equal to this. Okay, right. Right. Okay, this is the equation. Therefore, this equation will, that means W, that previous equation, thus this, as per this definition, W say, then the output signal, at each output signal of the receiver will be depends upon the probability function. That is, this equation will absolutely identified in the signals by elucidant spaces. So this is absolutely, you can say that. So that means from this equation, noise is irrelevant in the AWG channel, but that means output of the receiver is only dependent upon the probability density function. If the probability density function, since the noise component in the output as very basic equation, output has to be consistent with the input plus noise. Noise is 0, and the final end of what we derived. That means we can say this noise is irrelevant. The formally we can state that signal deduction. That means signal identification. Deduction means absolute identification of the signal at the AWGN channel is absolutely concerned only on the projection of the noise onto the basis function of the signal set. Yes, I am okay. Affect the sufficient statics of the decision follow the remember the noise. This is formal statement. You just simple is that A is considered only the noise we projected from the transmitter is equal to exactly from the transmitter it is equal to receiver, but it absolutely depends upon what exactly only the signal noise is equal to, that is exactly the noise is irrelevant. Now let's go back. What is exactly this is you learn it now. It's very clear. Once, please remember, capital X is equal to input at the receiver. Each input of the receiver, each elements of the receiver will be what exactly? It will be summation of the input plus noise. Input of the signal is absolutely of the signal. Each element of the input of the signal of each element will be identified by the receiver through probability density plus noise. Noise over the mean is 0. Only that means probability density function will be identified by the receiver in order to check the each element component of input is correct or not. That is why the noise is irrelevant in AWG, and you can understand why we are studying a signaling over the AWG channel is that at this topic, very prime objective of that, the noise is 0 in the AWG channel because the noise over the constant is 0. Now let's come back. One more very important point is next. Let's go for likelihood function. See what is exactly in the receiver. See what happening. See, look back here. We transfer in the transmitter, okay, from the receiver. See, look back here. So from the receiver, okay, from we receive the signal. So there are a way in statistics we can analyze the signal in a reverse manner. That means we can analyze the signal in the reverse, which analyze the signal or in the reverse manner, that we call as a likelihood function. Likelihood function. What does mean here? Look back with respect to the digital communication, we have a transmitter, we have a receiver, we have a channel connected between. From that, we are subset of a signal, SI of T, the information signal will be absolutely passed over this channel, and the receiver will be checked. So when you analyze each that receiver input is capital X, each capital X will consist of each element of the capital X will consist of what? The input plus noise component. Noise component is 0 because AWG channel we have put noise is 0, only depend upon the what? Signal. Signal is depends upon what exactly? The probability density function absolute this. So that means we need to analyze the received value function, received signal in terms of the function that our that function we call it as likelihood function. This is also quite helpful. Why? Because when you formulate the output of the signal, when you formulate the given signal in terms of the output, and we can also verify in a reverse manner whether it goes to the reverse manner from the the function you define at the receiver, it is goes to the channel, from the channel it goes to the receiver in a reverse statistical manner, which also helps us to cross check whether it's correct. That is why one of the function has been introduced, especially in the statistics, called a posterior probability density function, and second is what prior probability function, then it's exactly likelihood function, and also called maximum likelihood function. This will really helpful because in statistics, let me not talk about too much on this factors right now with respect. Please to understand, likelihood function is the function which is forwarded to the receiver. We can analyze this in a reverse manner up to the transmitter. Absolutely, we can verify whether the receiver or whether the received function at the receiver will match the function at the transmitter. If this is a case matches, you can say the information is also perfect, and that function which you represent at the receiver, we call it as likelihood functions. See, that is what exactly, this is a formal statement I'm giving that. What is exactly this is the function which analyze the given function in an inversion manner, statistical output, L of theta of x is equal to, this is the likelihood function, f of x is likelihood function is given by, this is the probability density function. See, look back, what is that? When you come back to the, when we come back to what exactly, when you come back to the output, when you come back to the output of the signal, each element, the element of the signal is depends upon one input of the signal what we derived in the last class, last 5-minute discussion. The output of each of the reverse of input only depends upon, only absolutely depends upon the, only absolutely it depends upon the what, okay, absolutely depends upon the signal which is has to be analyzed by the receiver whether the received correct is information probability density function or is the receiver not correct, because since the noise is zero constant over that. So this is the function which absolutely, this is when you say this the output of the signal is given thus. That means when you say likelihood function, expected likelihood function at the receiver is equal to the what exactly, is equal to the transmission which is equal to the, is equal to the what exactly, the probability density function of the signal which you mentioned the last. That means likelihood function has to be matched with what exactly, the probability function. This is exactly called likelihood. This is very simple. All the points are very, this is exactly we call it as likelihood function. Please mind what is a likelihood function. The likelihood function is the one which is the function of the receiver, from which we can analysis in a reverse manner from the receiver to transmitter, so that whether there is the signal, whatever the function defined the receiver is matches with the function with what exactly the transmitter. When it matches, we can say absolutely the information is correct what the receiver by that, because this is the ultimately each information we are going to send by the each information we are going to send by, we are going to send, we can going to send, we can going to send by the information, we can going to send by the information in the form of the probability density function which will be analyzed the receiver sections. Okay, exactly. So and look back here, absolutely at this point of view I would like to mention here, this is the probability density function has been given. Okay, look back in this, we are removed that n by t, because please remember whatever the x of t is equal to probability function which we are defined in the last section as being is equal to what, probability density function of the output has to be the likelihood function which need to be analyzed from a reverse manner of this. This is the equation which I am going to get it. So there are one other type of likelihood function, what we call it as log likelihood function. This is which takes the natural logarithm of the likelihood function. This is for some application. Definitely, when you take optimum receiver using current deduction, which will be completed. Next class, I will complete this second chapter because almost completed. One left with what I call it as simple, what optimum receiver current deduction maximum. See, this all is simple, which I have already made a note for you people, and definitely I will take the next class. Okay.
ಎಷ್ಟು ದಿನ ಏನು ಡಿಸ್ಟರ್ಬ್ ಮಾಡಿಲ್ಲ